Forum. My name is John D'Angelo, and I am a professor of chemistry and the coordinator and host for the spring 2025 season of the Bergren Forum. This is episode 3. Today's date is Thursday, February 13th, 2025. And for those of you attending the forum online here in Western New York, it's one of the few warm-ish days we've had in a while, though it is still somewhat wet. But thanks to our amazing facilities workers, it is safe to walk. As always, here in Nevins Theater or the Powell Campus Center, it is cozy and the coffee and tea are hot and free. Before starting, we have a few announcements. First, next Thursday's forum will be given by Shelley Frayne and Kerry Kautzman. The pair's talk will be on exploring the intersections of business and culture. There are some other announcements this week. For students interested in a summer job opportunity, AU is seeking peer mentors for the AU Advantage Summer Bridge Program. See Alfred today for more details or email Sarah Pratt at pratt@alfred.edu. An art show curated by Diabu Hubbard will open tomorrow at 6 p.m. in the Robert C. Turner Gallery. The show is titled Threads of Her Story, Black Women in Art. Submissions are open for the annual Phi Beta Kappa Wit and Wisdom Competition. The winner will receive a $250 cash prize and present their award-winning work at the April 24th Bergren Forum right here in this room. The deadline for submission is February 21st, next Friday. Email Professor Juliana Gray at gray@alfred.edu for more details or find the guidelines on Alfred Today. If you'd like to live in the language house with a French native speaker and other French-speaking students in the 2025-26 academic year, contact Professor Bouhet at bouhet@alfred.edu. That's bouhet@alfred.edu. Submissions are due to Janet McLean at mclean@alfred.edu. That's McClain@alfred.edu by the end of March. See Alfred Today for the application form. Kudos to the Alfred University Food Pantry for earning platinum member status from their partner agency FoodLink. Thank you for supporting our community, and thank you to all who have supported the Food Pantry. Finally, sadly, former Assistant Professor of Education Corey Burdick recently passed away. There will be a celebration of life this Saturday at 2 p.m. at the Union University Church. Corey requested that attendees wear pink. There's no really good segue, but today's forum will be given by Kelly Kirtland, Director of Data Science at Capital One. Presenting is Attention All You Need, peeling back the layers of GPT-3. Take it away.
Hello, and good afternoon, everybody. Thank you for being here. As John said, oops, this is coming through. Oh, let's turn things on. How do I do that? Check, check. Is it working?
Yeah.
Hey, we've got sound. All right, awesome. So as John said, my name is Kelly Kirtland. I am a director of data science in the Model Risk Office at Capital One. I have been there for now about 5 years, 5.5 years, formerly of the Alfred University Math and Computer Science Department. So it's nice to come back, and it almost feels like being back home a little bit. So I wanted to talk a little bit about GPT models. GPT models are a class of large language model, or LLMs. The first that really made a notable splash was the GPT-3 model. So you might ask, why are we going to look at that one? It's so out of date. Everyone's into all the newest, latest, and greatest things, GPT-4, GPT-5, the llama models, you know, the stuff coming out of China. And then the reason is fairly simple. Number one, it's been around a while, so we know a lot about it. And two, a lot of information was published about it, whereas a lot of the newer LLMs that are coming out in research don't have as much information available. But understanding what are the different component pieces that are making up the GPT model can help us to understand what are the opportunities that have led to further improvements in these future models and the potential improvements that are still available in large language models. All right. So I'm going to say, and this is an undersimplification, that GPT models are really based off of 3 primary breakthroughs. Now, these are breakthroughs in like the modeling sense. There is certainly a sense in which technology and infrastructure also needed to be developed in order to allow for this, right? Compute power, memory, data storage, and pipelines. And I'm going to talk about none of those because that is not my area of expertise, but absolutely an essential part of having large language models and generative AI functioning as we know it today. So I'm going to talk about first, what's the background? What's like the general framework, the class of models that LLMs come from? What did they look like in the past? And what are some of the challenges that you face in extrapolating that out into language? Then we're going to try and talk about the different things that have led to solutions to those challenges in language. Embeddings, multi-head attention, deep learning, and then we'll kind of put that all together into how GPT-3 utilizes them and talk about why it is that this structure allows us to generate language the way that we can now. All right, so the autoregressive plow. Let's start with a little language lesson, right? Auto means self. Regressive means backwards. So an autoregressive model is one that looks backward upon itself, right? It uses past information as well as past predictions as it moves forward in time in order to predict the next thing that comes up, right? This has been used classically in a lot of different varieties. One of the most common is stock valuations prices, but you often see things in science and geology, right? Temperature, inventories in stores, audio signal processing, traffic flow patterns. A lot of these things are related to each other in terms of how the history informs the future. So this is an example that comes from astronomy. This is sunspots and total solar irradiance levels and how those relate to each other in time. One of the classical things that you see in typical autoregressive problems from the classical modeling sense is that values that are close to each other in time, and this can be extrapolated to space as well, tend to be similar in value, right? Knowing the level of solar irradiance from January of '88 is going to be more useful for predicting what it's going to look like in February of '88 rather than looking back to '83. And you can kind of see the same thing in temperature. Right now, it's relatively warm for Alfred in this day and age, right? In February, it's probably in the upper 20s, right? So getting a little warmer. Tomorrow, we're probably not going to say that 65 is a likely temperature. 65 is a normal temperature that we see in Alfred, but it's probably not going to happen tomorrow because temperature doesn't swing that drastically in that quick a period of time. So classically, recent values are going to be more predictive of the next value. So we look at the recent past and weight that more heavily than the more distant past in order to understand what's going to come next. All right, so here are some challenges that we face in language. The first, when we talk about values being similar to each other, this makes perfect sense with numbers. 2 is closer to 5 than it is to 20, right? Pretty easy. We can exactly talk about how, yeah, that's good math, thank you. So how do we measure word similarity though? That becomes a little bit more complicated, right? Is closer to run than it is to book? I don't know. That becomes a little bit messy. And then the third is that language is very dynamic, right? It's not perfectly predictable. So how do we leverage some of this dynamic aspect, right, to keep it from feeling robotic? All right, so we're going to tackle these one by one. We're going to start with embeddings. Language is complicated. So the first thing we need to do is we need to break it up into pieces. And letters are not the most useful pieces of language that we can use. Typically, we break it up into chunks that kind of more or less correspond to words. There are different tokenization procedures. They don't all break up language in exactly the same way. Here are 2 examples with text embedding and the Gemini tokenizers. And you can see that some of them are the same, like weather is its own token in both of these tokenization processes. But if you look at, say, raining under the text embedding tokenizer, ing becomes its own meaningful chunk. it contains in itself some component of meaning that we're going to extract from the word rain, as opposed to in the Gemini, where raining is leveraged as an entirety. So tokenizers, there are different kinds. We're not going to go deep into tokenizers, but once you've divided things up into chunks, you're just going to give everything a label. And because we're going to be passing these into computers, we're going to give everything a numeric label. Computers are much better at processing numbers than they are at processing letters. So we're just going to assign everything a number. However, you can have the same token mean different things, right? The bat didn't bat an eyelash at the sound of the baseball bat. Those are all three different words, and we understand that. The computer doesn't, right? It just says bat is 168,692. That's its label. And it is the same label no matter how it's used. So we're going to use embeddings in order to take these tokens and try to imbibe context into them, right? If you are familiar with vector algebra at all, we can take vectors, which function like little line segments. You can imagine them as little line segments emanating out from the origin here, that center point in the middle of our set of axes. And we can say, well, vectors that are close in angle, like they're pointing in more or less the same direction, we think those are similar to each other. So we're going to look at angles between vectors to say words are similar to each other. There's also this cool thing that happens with embeddings, which is that changes in the direction have their own kind of semantic meaning. So you can kind of look at these two embeddings, uncle and aunt. They have a very similar difference between their tips to what we have between man and woman. So this direction, that amount of change that we're seeing in the vectors, corresponds pretty closely to just womanization. We're going to take a value and we're going to make it more feminine. And it's a very curious thing that happens with embeddings, but when we use embeddings, we use very high dimensional spaces. The more dimensions you have, the more information that you can capture, right? You can kind of look here. We have some vectors that are kind of pointing up and down. And you could imagine that there's this flashlight that's over top of it, and it's projecting the image of these vectors down onto this piece of paper, this plane down here. And there's an angle between that. These vectors are further apart, though, in angle. There's a second angle up here than these. However, if you took a flashlight and projected those angles down onto the same piece of paper, those little line segments, the angle between them on this piece of paper looks the same. So the more dimensions we have, the more ability we have to capture complex ideas within the space. We can also imagine, so each token has a single embedding, right? So again, we do still have this idea of one-to-one, right? The bat, 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 bat. They're all going to have the same embedding, but we can imagine that this embedding is really just an aggregate of multiple embeddings that have different meanings, that have moved in these other semantic directions. So here's an example where we look at the word mole, right? The chemists probably immediately go here, right? 6.02 times 10 to the 23rd, right? The mole. Anyone who's in zoology probably thinks of the animal. And anyone who's an esthetician probably thinks of a beauty mark. All of those correspond to the word mole, and we can think of the embedding as capturing all of those different semantic meanings that we use in language and just aggregating them into a single vector. All right, this is from a pretty awesome paper by Chen, Hula, and Dvorak, where what they did was they took all of the sentences that contained a particular word, in this case, sheet. And what they did was they created these embeddings on those values, and then they did what we talked about. They just took angles between them, said ones that are closer to each other, we're going to group into these clusters. And you can see that some of them make a lot of intuitive sense, like this one, sheet. music, songs, song, guitar, piano, library, published, MIDI. So you can kind of see that there's a semantic meaning captured in these clue words that tell us about how we should interpret sheet. There's a different set, right? Paper, glass, one, thin, ice, single, plastic, right? This gives us a different semantic meaning, right? We may need to move our embedding in a different direction in order to capture these things based on the clue words from context. So this is kind of moving us into that next phase. So contexts in the embeddings capture and aggregate all of the information available that we have from the data we have used to train the model, which for GPT models is a lot, like the entire internet. All right. So, okay, we need a process to extract these context clues, right? These would be context clues that would shape and move the way that we want that embedding to move in space. So that brings us to breakthrough number 2, multi-head attention. The seminal paper, as it's considered in terms of large language models, is referred to as attention is all you need. It's a very dense paper, but if you are mathematically minded and really like a challenge, I recommend reading it. There's a lot of fascinating stuff in it. But what this is doing is it's providing us a mechanism by which we can address the fact that context can happen anywhere in the past, right? It's not necessarily the previous word or the previous 2 words. The important things might be arbitrarily far back in the history of what the model is taking in as input. So I took some very simple ones, right? What words are most important in order to understand Harry in these 2 little parts of a sentence, right? For a wizard, Harry, and Sussex is for Harry. We have a lot of the same words, right? For is in there, Harry is in there. But we would probably say, in this word, I think wizard is going to be the most useful for telling us about Harry. Who is Harry? Which one are we talking about? In this one, I would say Sussex is probably the most useful for telling us who are we talking about? Harry who? However, that's not the only question we can ask of the past, right? We might be interested in which Harry this is, but we might also want to know, is Harry the subject? Is Harry the one we're talking about? Are we going to be speaking from Harry's perspective for the rest of the sentence? We could talk about all kinds of other things we might want to know about Harry. Does Harry refer to an animal or a person, right? There's a whole bunch of questions we could ask about words from the context we have in the past. So how do we get at those different pieces of information? The central idea is that when you think about a vector, you have to think about it in context of the space in which it resides. It has meaning within that space. If you take it out of that space, it then has a different meaning. You want to make sure that we think about these vectors in these spaces. Okay, so what we're going to do is we're going to use these things called queries and keys in order to convert from the embedding space, right? We already talked about what the embedding space does. There's a whole set of meaning associated with that. And we're going to take both the word that we're interested in and what we have available to us in order to predict what comes next. And we're going to convert to 3 different spaces. One is called the query space. And you can think about query as a way of asking a particular question about the last word we have in order to understand what it is. And understanding what that last word is going to help us know what to say next. The key space, this is what tells us what is going to be useful in the history. And then we have the value space. And I'm going to be honest, this was a little bit of an oversimplification over here because I'm kind of combining 2 spaces, the value space and the output space, but we're going to pretend that's not true. And we're going to pretend that the value space is going to give you the information about what each of these words would mean. So maybe the word for indicates we're talking about Harry as Truman. Maybe A is most often connected to Harry Styles. Maybe just Harry, most often we think of as Harry Houdini. That's the first person who comes to mind. But when we see wizard, Harry Potter is what we think. So we're looking at these and saying, all right, we have these different possible values. The key spaces is what's going to tell us which one of those to use. Query spaces how do we know which of these values or what we're interested in knowing about it? All right, this is the worst slide that I have, in my opinion, but it helps give you an idea of like what we're doing. Anyone who's taken linear algebra knows that whenever we're converting space to another space, we're going to use matrix multiplication. So we are going to build query and key matrices out of parameters. Parameters are basically the set of knobs that you're able to twist and turn in order to get the model to work the way that you want. And we're going to use these parameters to create these queries and to create these corresponding keys, and then the values that extract from it. And then you have these multiplication things which go in these different spaces. We're not going to talk about softmax too much. But once you have like these keys and queries, self-attentions, this is basically the importance matrix. You can see like darker things mean it's going to be more important, lighter things means it's less important. And then we're going to put that together with our values, and that's going to give us these context vectors or the output space. And that's going to be informative for telling us what should we do next. All right. But each of these things, keys, queries, values, each of those little dots is a number that I don't know what value it means. Queries are not really interpretable. We can't take something and say, are we asking if this is an adjective, a noun, or a verb, right? We can't tell what we're saying. These are things that are tuned and learned by the model. Okay. Each key, query, and value matrix only corresponds to answering one kind of question. If we use multiple of these all together, right, put a whole bunch of these key, query, value patterns together in the same kind of structure, we can get a lot more information about the word, the last word we have in our context, the thing that's going to help us determine what should come next. This is what's referred to as multi-head attention, right? What we did the last time in that super confusing, this is one head. We want to just pile a whole bunch of things all together and ask a lot of questions. So we use this multi-head attention, and that gives us a bunch of different pieces of information from the things in our context that would provide that kind of that information. Okay. So we have an understanding of embeddings. We've explored multi-head attention. We're going to talk a little bit about deep learning. Deep learning, I would say embeddings and deep learning are both relatively old. Multi-head attention is newer. So you're probably somewhat familiar with this. If you ever heard of a neural network, then you are familiar with one form of deep learning. This is not the only place where we see this used in large language models, but it's probably the one that has the most importance, is where I'm going to focus, is this called the feed-forward layer. This allows us, right? So multi-head attention is pulling information that we have from context. The feed-forward layer is pulling things that we know from the world, right? External information. There might be information that we have about the world that is not purely contained in the words that have preceded the last word that was said. You all come with some level of information about the world. The feed-forward layer is where we're going to utilize some of that information. So we have these complex relationships that are, again, learned from the world. Again, this training data set, which comes from like the entirety of the internet or a whole batch of just language and words that we've thrown at this model in order to get to recognize these patterns. And it introduces nonlinearity. Nonlinearity is essential in order to have a non-robotic form of generative language. Right? This is the thing that really drives it. So in the GPT-3 model, for example, this is where you get they use the GELU, the Gaussian, I don't remember what the E stands for, linear unit. The most common one you see in neural nets is ReLU, which is the rectified linear unit. And we'll talk about how those are used, but you're going to take some inputs, you're going to do some transformations on it, and you're going to get some output. So what is that doing? So we're going to take a look at one example All right, so this is a very simple neural network. It has only a single hidden layer, all right, with 100 perceptrons. These are just kind of things in the middle. And these work functionally like dimmer switches. They're either off, or they can be on a little, or they can be on a lot. And that activation function from the last slide is what tells you about how bright this perceptron is going to be. And similar to the way we think about that self-attention, this is telling us about the importance of a particular piece of information. Okay, so the context of this picture is we have a set of dots in a flat X and Y plane. So we have two inputs, X values, Y values. What we want to do is we want to get to the point where each of these swirls on the spiral corresponds to the color as designated here. So if I were to put in a random spot, we'll say there, that one doesn't exist yet. I want to give that a color. How do I assign it a color? Well, if we were in classical problems, all of the things we've done up until this point, you only have lines to work with. We want to take this and we want to divide this up into straight lines. That does not work well with a pattern like this. This is a non-linear pattern. So introducing nonlinearity allows us to capture some of these complex patterns. So what are those perceptrons doing? I'm going to skip over a lot of math and say, if I were to draw on my original X and Y axis, where I think things belong, what color I would assign to them based on my image in my head, right? So you've got this yellow slot, anything that falls within that color. If I put a dot there, it'd be red. If I put a dot there, it'd be purple. Once it comes out, look at the way that you get division between these different groups. Over here, they're very curvy and bendy. Over here, you have lines. What you've taken is you've taken a space that was curvilinear, and through the process of leveraging pieces of information here in the perceptrons based on particular qualities that exist within the X and Y plane, and activating certain components of it, we've enabled a linear division of a new space. And you can see all these curvy lines. Those are the axes from the last one. I know, it's a little trippy. So what we've done is we've taken the space that existed over here and we've bent it around in all these strange ways so that now we've got linear divisions. It's a lot easier to predict what's going to go where. All right. There's a lot we could say about deep learning, and there's a lot that I'm not going to say here due to time. So let's talk about GPT-3. How do we put all of these things together into a component? So we start with, you have an input, right? I've been using this word context. Context is all of the input that we're going to give to, we'll say the chatbot, right? Which is really built on top of a large language model, but we'll say that. So we've got context, right? That's the history that we're going to pass into the model as our input. And we're going to take all of those things and we're going to convert them to their embeddings, right? We're going to divide them up into their tokens. We're going to convert their tokens to their embedding values. So this is basically just a lookup table, right? We're not doing like a model fit in this step. We're just saying, here's the token, look it up in the matrix, there's my embedding. Then we're going to put together multi-head attention, which is again how we take information from the context and update our embedding, right? We take our embedding and we can push it in these different directions to capture these different ideas that are included within our embedding average. And we're going to allow that to be pushed around. And then we're going to use that feed forward layer. And we're going to take information that we know from outside of the context. What do we know from everything else we've ever looked at? And we're going to push that embedding around a little bit more. And then we're going to, this combination is called a transformer. And then we're going to do that a bunch of times. We're just going to do it over and over and over and over and over and over again. In GPT-3, there are 96 transformer layers. Then we're going to do a prediction step. There's some flexibility here. Sometimes you can say in your prediction that you want GPT to just always give you the most likely next word. You also have some flexibility to let it be a little bit more, surprising and say, oh, just pick any of like the top 5, and then you can get a little bit more dynamic in your language. So there's some fun stuff that happens in prediction. But then once you have a prediction embedding, you say, okay, this is the vector that I think most likely comes next. Then we unembed it. We're going to convert it back from an embedding to a token. We're going to use that token to look up what's the word, and we're going to print that word. So often when you see GPTs happen, right, they happen word by word. So one word will appear, and then they'll use that word along with everything else that came before it. And they're going to run through this whole thing again. And then they'll give you another word. And then they're going to take that word plus everything that came before it, and then they're going to run this whole thing again, and they'll give you the next word. So that auto-regressive process still exists, but you have this significantly more complex process by which you're making your predictions. We defined the word parameter before. Parameter is the set of like knobs that you can tweak the value up or down. The value of those parameters are the things that are learned through the process of training a model. The more parameters you have, the more flexible your model is, the more complicated relationships you're able to capture. So in GPT-3, you have about 175 billion parameters annualized, which is a lot. There's many parameters. This flies in the face of everything that every model builder that has ever been trained on classical statistics knows, which is you don't want to overfit your model, right? If you make your model too flexible, it'll just follow exactly what your input data was, but then you give it something new, something it's never seen before, and it just goes off the wall. It's like, I don't know what to do with this. It gives you the most absurd prediction ever. Overfitting is like the bane of every model builder's existence. And yet, for some reason, this model with 175 billion parameters doesn't seem to have that problem. It's a very counterintuitive thing. It basically just flies in the face of classical statistics and says, you know what? If we just make it big enough and complicated enough and train it on enough information, we don't have to worry about that too much. And that is, I don't know, frankly, very surprising to me, but seems to be true. So if we look at how much each of these different component parts contribute to this 175 billion parameter process, right? We have the embedding and unembedding process. So we have matrices, embedding matrices and unembedding matrices. And together they make about 1 billion parameters in those matrices. Multi-head attention has about 58 billion. The attention space has been predefined to 128. The embedding space is 12,288. But there are 96 heads of attention within each multi-head attention box. And then there are 96 layers, and each of those heads of attention has 4 matrices. So that's a lot. And then the feed forward matrix, I didn't talk about the matrix type that go into there. There's an up matrix and a down matrix, and there's a little bit of complexity there. So we're not going to talk about that. But in the embedding space, we have the number of neurons multiplied by the embedding space gives you the number of parameters you have there. For each matrix, you have 2 of those matrices in 96 layers. So you have this very large model, which when you look at this, it also, again, flies in the face of that name of the seminal paper. You remember, attention is all you need. But if you look at the numbers, where is most of the information coming from? It's coming from information that doesn't come from the inputs. It's coming from the training of the model, right? Context is what you have asked ChatGPT to do for you. You've put in something that says, I am trying to write a paper on the influences of French society in Costa Rica. I don't know, whatever. Trying to do something. I want you to write me 8 paragraphs that touch on the economic and political influences that have impacted Costa Rica from French society. That's the context. Where is it pulling this information from about what is it going to put in about Costa Rica? It's pulling it in from everything that the model has ever seen about Costa Rica and French influences. And that gets captured in that feed forward layer. So I know that this was quite a lot. And you're probably coming out of this thinking one of two things. You're either thinking, man, I really understand how LLMs work, in which case I have failed you. The other is, man, I really have no idea how LLMs work, in which case I have also failed you. I hope you know a little bit about how LLMs work. I will say it was one of the most challenging things I've ever done, writing a whole talk on this with no equations in it at all. It really flew against the grain. But there is a sense in which we cannot understand how LLMs work. If you come out of this and say, you know, oh, all these people who are building these things, you know, they can tell me exactly how feed forward works. If anyone says they can tell you how feed forward works, they are lying to you. It is so complicated and so convoluted. No one knows exactly what's happening in all of those neurons and how the GALU activation function is operating, or what's the meaning of each of those neurons, right? I don't know. It's so vast and so big. We cannot comprehend it. That being said, let's talk about opportunities for LLM. So this is all from GPT-3. Many, many things have happened in the large language model space since GPT-3 was introduced. We have a lot of opportunities for improvement. Again, we hit this success of like ChatGPT works and does good things because we just decided, throw out this concept of overfitting, throw everything we can at it, bigger is better. But now the question becomes, how much can we pull that back and still retain the same amount of performative, excellent performance in terms of predictions without spending as much time, because these large language models, by their very definition, take a lot of time to train, right? It takes a long time to figure out what is the exact right value for 175 billion numbers that can all be adjusted in any direction, in any amount. It takes a lot of time. It takes a lot of memory to store this. It definitely has an ecological impact, right? It's extremely, it goes against every green action that we ever want to take because it takes so much energy to process this. And once you have 175 billion parameters, when you're running the thing, there's a lot of lag. It's slow, right? If we can simplify this somewhat, we could have a model that predicts things faster. It's faster to build and train and more efficient. Doesn't cost as much money, doesn't cost as much time, doesn't cost as much energy to do. So how far can we pull that back? And that's a lot of what we're really seeing. There are also other improvements that you can make, which is a little bit trippier, by saying GPTs are purely autoregressive. They only look at things that have happened in the past. There are models that exist, even in the generative AI space, that look both backwards and forwards. So like you predict some things and then you kind of look backwards and then you update what you had previously created. That's a whole different thing. I will say that the attention is all you need. So the self-attention process we've talked about here is for generative within a single language. The original context of the multi-head attention was in language translation. So there is this component of cross attention that happens because the ordering of language isn't always the same. And like if you're trying to translate from French to English, the way that nouns and adjectives are ordered in space. So sometimes you do need to kind of move things around. So language translation functions slightly differently, but you can leverage a similar kind of idea in prediction within a single language. Becomes a lot more complicated, but allows for even more effective and lifelike predictions. All right. So here's the basic summary of what we've done. GPT models look at what's come in the past in order to predict what's coming next. They also include looking at what they have previously predicted to inform what they should say next. Embeddings, we have captured a way to enumerate words, not only by themselves, but also how they exist in relation to all the other words in the vocabulary. Multi-head attention allows us to remove recency bias and allows us to pull information from past context words wherever they exist in the context. And deep learning incorporates complex information that is from outside of those input values and can be incorporated into the generation of language and the predictions that come next. And then GPT-3 shows us that classical prediction problems, apparently, surprisingly, can be overcome if you just make your model big enough. There is a set of resources that I found especially helpful. There are academic sources that I think are useful. Attention is all you need. Again, the seminal paper in large language models from 2017. Language models are few-shot learners. That is the GPT-3 paper. And then how do transformers learn topic structure is just I don't know, it's just fascinating. It's hard to really explain why I like it. But if you don't feel like reading academic research on LLMs, if you don't really like doing a bunch of matrix multiplication or see complicated equations, I say go over here. These are the places where I found, I would say, most of my imaging. The neural networks course from 3 Blue 1 Brown, highly recommend. Let's build GPT from scratch in code spelled out for those of you who are programmers. And then there's a Stanford course by Jarofsky and Martin called Speech and Language Processing, which there is a ton of information available there. It at least breaks down the academic sources a little bit more for you, but is still going to be a bit more high level for those of you. So, all right, with that, are there any questions? Yes. Oh.
How would you summarize the difference between version 3 and version 4?
Yeah. I don't know what's the difference. I think they used a very similar structure. I don't have at the tip of my fingers what the parametric form looks like in terms of its relative size. I believe GPT-4 was just bigger. They had more compute power at the time, so they were able to capture a bunch more information and able to make it bigger. I think where you really start to see a paring back of the parametric space is more in what we're seeing coming from out of China in like more recent times. Yes.
How has open source models such as DeepSeek affected the Capital One and the finance industry, and can it benefit from it?
Can the industry benefit open source? Okay, this is a very interesting question, and the answer is it could both benefit a lot and it could also be harmed a lot. So as with all generative AI, there are a lot of pitfalls. The most in terms of OpenAI, I'd say the two biggest risks in the financial industry are hallucinations, which is basically when models just make up a bunch of stuff that isn't right. And if people are leveraging the output in an uninformed way and acting on these hallucinations, you can make some really expensive mistakes. And then the second is related to cybersecurity. Anytime you're leveraging open source models, there's a risk of data leakage, in the sense that information you provide as context to the model in order to perform an action may be then available to the creators or contributors of that open source project or anyone who wants to utilize it, like if it gets incorporated into the training data. And there's a lot of risks associated with that, right? There's sensitive information that banks hold, and you want to make sure that that is maintained very closely. So one of the things that my team does in the Model Risk Office is we have set policies for how large language models are going to be utilized within our bank, and in order to try to address these issues.
A little glossary help. I had always heard about generative AI, and now in the last week or so, I've started hearing about general AI. Can you explain what's which?
So I don't know the term general AI in context, but I would say if I were to guess or hazard a guess as to what the difference is, AI is not only useful for generating language. I think one of the primary uses that I see in terms of minimizing the risk of hallucinations that we just talked about is in summarization rather than like creation, like direct quotes from source. Classification is also a potential use case of AI. Like, what kind of document is this? Is this an academic literature? Is this a course? So if I were to guess, because it's not a term I've heard, I would say it's that concept, that these large language models can be used for a variety of different purposes that aren't all about generating text.
This is more of a comment rather than a question, so shameless plug.
Do it.
I have a paper actually on writing infinitely many activation functions. So it's a published paper. Essentially, if anybody knows about behavioral economics, it's a translation from behavioral economics to activation functions. But again, although we know exactly how neurons would work, but the problem is they just have a classification, binary classification 0, 1. And why would that binary classification be so effective is not known. There's no mathematical proof of why, even after classification, the system works. And the hallucinations which you are talking about is essentially leading to the answer that there's probably never going to be a proof of why this thing is effective, because there's always a possibility of correct answers.
Yeah, like one of the biggest challenges with LLMs is how do you assess its performance? And I'm really curious about, like, did you have performance assessments on these?
No, it was just a theoretical paper. So it's about like, how do you generate infinitely? Because you just have a finite, if you go to Wikipedia, there's only a finite list of activation functions. But my paper gives infinitely many. But the problem is, again, so that was the problem I faced when I was published it, because it took me like 3 journals to publish it, because everybody wanted a performance thing. If you have infinitely many functions, why one should be better than the other? Eventually, I published in another journal, but the point is exactly, there's no way to know.
Oh yeah, no, there's no way. So how do you pick which activation function you're using? I mean, the current methodology is just what's the easiest for the model to learn from.
Yeah,
right?
again,
What's easy.
Yeah, I do not know. It's just infinitely many activation functions, but it does not give any procedure of what is the right one you pick and why it is the right one. And I tried to work on it, and it is not possible to generate, because for activation function just gives you whether, when you train the network, it tells you what data you want to choose and what data you do not want to choose. It's very binary.
Yeah.
It's either rejected or accepted based upon the weights. And so you can make multiple layers, but again, it does not show you, depending upon what you choose, will completely change your output. But there's no way of saying that one output is better than the other output.
I challenge you on the last point, which is, I don't necessarily know if it would significantly change the output, right? You can see very I mean, again, it depends a little bit on how things are structured, and if you're always taking like the argmax in the prediction step, right? How are you doing this? Like, is it more flexible or is it not flexible? But in practice, I have not noticed a significant change in the use of different activation functions in the sense of what is output or what would be leveraged. And I think this gets to that idea of like correctness in a model, which is there such a thing as like correct or best? Like, probably not. And in the context of large language models, the selection of the activation function is arbitrary, similar to the dimensionality of your, could be your embedding space, could be the dimensionality of your key query space. All of those things are just numbers we just pull out of the air. We pick it because we think that the computer will be able to handle it at this moment in time. And again, this bigger is better idea. But when you have this much complexity and when you have this much flexibility within your model, when you see differences in how activation functions operate, I don't think the influence of the activation function is that important beyond the scale. So yeah, I don't know. It's a curious one, but I can see why you wouldn't have necessarily these like outcomes within a paper like that. And I think it is a good point that activation functions are an arbitrary construct in how we utilize them in space.
We have time for one more.
Yeah.
Kelly, first of all, thank you very much. I thought that was fascinating. I also want to assure you that I don't think I understand how AI works, so you didn't fail in that direction. And so this question, I don't really expect you to know. I'm just curious if you've heard or you happen to know if our brains are essentially doing something very, very similar to this. Are our brains, when we're thinking, also just kind of picking the next word, like predicting based on all the stuff we've put in our brains before what the next word is supposed to be? Or is this a very different model of coming up with the next word?
So I do not have expertise in this. Based on my experience having a brain, I would say this is an oversimplification of what our brains do. I do think the concepts of taking what we know from the past and what we know from outside context are similar. But when I think about language and generate it out of my mouth, I usually have thought at least a few steps ahead and I'm going backwards. So I think those models that leverage that like forward prediction and then backwards updating, I think would be similar. But in terms of like activation functions and how that all works, like, I don't know about that, but that would be my guess, is that the GPT style, which is only retrogressive, is a little bit more simple than the way that we think.
We are butting up on time, so if there's any other comments for other people who have to go.
Yeah. Yes, you do see neurons firing, but that's just what we're able to image when we examine the brain. We don't exactly understand what's happening with these neuron firings. So I'd be hesitant to say that this is quite similar. Yeah.
Please join me in thanking Kelly for a great talk and see you next week.
Hello.
This is a dumb question, but is it